In this video, we are going to talk on the state and theorem of existence and uniqueness. We have let f of xy be continuous on a domain of the xy plane, and let m be constant shows that f of s y is less than or equal to m in domain I is equation 1. Then let f of xy satisfy in domain of the elliptic condition. Know that elliptic condition, if it satisfies this, so it's a elliptic condition. Equation 2, where the constant k is independent of x, y1 and y2. Let the rectangle how defined by this x minus x less than or equal to h, where is whenever we see anything less than or equal to h, then the absolute value of y minus y less than or equal to k lies in D, that is domain, where mh is less than k. Therefore, s minus s naught is less than or equal to h. The differential equation y prime is equal to f of xy has a unique solution. Then f is equal to y of s, for which ys naught is equal to y naught. We are still to prove this. It means this is the state. We have to prove the what? Existence and uniqueness. So it states that this existence, if you have this function of all this, is satisfied that it exists, and if you have y prime is equal to what? F of xy, it means a unique. So this one means when you have a function like this, when you have a function that stays like this, it means the function of the solution is what? Is unique, and this is the what? This is the state on what? On existence. So in existence, we have 4 steps we are going to show before to prove that it's this function let of f from f of xy to here is what? Is existence. And we have 1 step to prove on this, that this differential statement is what? This differential equation is it is unique rather. So in our first steps, we have that, okay, first step is what? We have to show the functions lie in the domain. The functions lie in the domain D, and it is well defined. So for us to prove the existence, we have to show that the functions lie in the domain D and it is well defined. Then we have to satisfy the following inequality. For we given an inequality of less than or equal to mh, this equality, we have to satisfy them that we have to show the function of the inequality also exists. And then we have to show that if n turns to infinity, the sequence y of n converges uniformly. The last one is what? We have to show that this y of s, the y over ds will give you what? F of xy, that is the y will give you y of s satisfy the differential derivative or differential of the y over ds will give you what? F of xy. Then you now satisfy that this y prime is equal to what? F of xy. You still have a unique solution. Then if you show that this one have a unique solution, when you have a unique solution, as I explained previously, I explained that it must be continuous on what? On the initial condition I will give you. The one that I explained in our previous lesson is what? Picard existence and uniqueness. It's also something related to this. You can see in that one we are giving the state, that is state that, and we will now show it with example. But for here we are being given states related to inequalities or this. There is a different way we can prove Picard uniqueness and existence theorem. So in this one you can see that this is what the state. So it depends on the state that they were giving us, we are going to determine. Suppose we are given to prove that it is continuous on f of t naught and y naught, we are going to use that previous explanation. And if it is also continuous on derivative of f with respect to y, and it is continuous, that it is unique, we are going to use the previous explanation to solve it. And we were given example that I showed that it satisfy unique and existence, and one satisfy unique, one exists, and the second one is not continuous, that it is not unique. So in this one, we are being given the state, that is existence and uniqueness state, that all this for what? So for us to prove for existence, it means we are going to show 4 steps on this. So on our last step is what? To satisfy that derivative of y with the y prime is f of x y as a unique solution. So our first step is to what? Our first step to show that it is exists is what? We prove that the function lies in the domain. Thus the function f of xy lies in the domain. And in the statement we are being given, because of time and this board cannot contain everything, so that's why I was uploading it, or it was displaying on the screen. So we'll be following on the screen the proof, and I'll be showing how they got it. So in that proof, we have that let x be such that x minus x naught is less than or equal to each. We now define a sequence of function y1 of x. If y1 of x, a sequence is just something going in series, y2 of x, y3 of x till yn of x. We call it we now call the successful approximation as follows: y1 of x is equal to y naught plus x naught integral x naught to x fx naught x y naught dx. What they did there is from Picard additive method, we get that our yn of s will give us y naught plus from s naught to s f of sy yn minus 1 dx. So if our n is 1, as our n is 1, we are going to have y1 of x is equal to y naught plus s naught to x f of x y n. If our n is 1, so here we 1 minus 1, I'm going to have dx, which stated that our y1 of x is equal to y naught plus s naught of x f of x 1 minus 1 y naught dx. You can see it from there that that's why they get y naught dx. Then if I do this for 2, if I do this for y of 2, I'm going to have y of 2 of x is equal to what? Y naught plus for s naught to x f of x. 2 minus 1 is y1, so y1 of dx. So if I continue doing this, I'm going to have yn of x, then y naught plus s naught to x f of x yn minus 1 dx. So you can see that we want to show that the function lies in the domain. So you can see that the next step is like we now prove that for s minus h less than or equal to x minus s naught plus h, we have been given like we prove that s minus s naught h of this less than or equal to this y minus y naught less than or equal to h is what? The curve lies in the rectangle. It can be rectangle, it can be domain. That is, our y naught minus k is less than or equal to y minus y less than or equal to y naught plus k. Now, what they get? So for them to how do they get this state? How do they get this solution? They said now they have y absolute value of y1 minus y naught. How do they get y1 minus y naught? They got it from here. This is our what when n is 1. We are going to have y1 of x y naught plus s naught of x f of x y naught dx. They take the right hand side, y naught to the what? Left hand side. So I'm going to have y1 minus y naught. y1 minus y naught will give me s naught of x f of x y naught then dx. This is what they did there. You can see from there. So what did they do next is what? They now take the absolute value of both sides. When they take the absolute value of both sides, taking absolute value, taking absolute of both sides, value of both sides, What did they have? So y1 minus y naught, the absolute value of this, will give me s naught all over s f of x y naught dx. So I have this something like this. You can see it from there. That's what we have. That's how they got it. So my next step is what? What did they do there? So this equal to change to what? Less than or equal to. You can see it. When this equality sign to less than or equal to, yes, it can change because we stated that f of xy is less than or equal to m. So for it to change to from equality set to less than or equal to, it means our this absolute value is going to be what? It's going to only affect the f of x, y, not the s, not integral. S not all over x because of the what? Less than or equal to sign. So I'm going to have, so that's why we have it from there, that we have y minus y naught. We have y minus y naught. Y minus y naught from here, then integral s naught to x. We have f of what? S y naught ds. Something like this. So, or another way is e, or y minus y naught is equal to m, then s minus s naught less than or equal to m h less than k. Do you know how they got it? What they did there is that, how did they got n less than or equal to m less than or equal to y m h minus k is they got it from here. Whenever we have anything related to our f of, whenever we see f of s y naught, f of x y, something like this, less than or equal to h, we are going to substitute m inside it. So from there we are going to have y minus y naught then is less than or equal to s naught x. Then whenever we have f of s minus 1, I'm going to have m, then ds. I'm going to have ds as well, because this absolute value is affecting ds too. So they separate it outside. So from there, we are going to test for the two. We are going to test less than or equal to. So from here, we take this one outside. We are going to have less than or equal to m, then s naught. M is to take care. So we are going to have s naught of x, then dx. So you can see from there, we have it. And also they are less than or equal to, if you find the integral of this when x, we are going to have ms minus m naught. That is m minus m0. So that's why you will see it from there. You are going to see m x minus s naught, then ds. So from there, less than or equal to, whenever we have something s minus s naught is related to, you can see that s minus s naught less than or equal to h, y minus y naught less than or equal to k. So you can see here that we now have m s minus s naught less than or equal to m h k. So less than or equal to m h and what? Less than or equal to k. So you can see that this is what we are proving, this that, and from this we get less than or equal to m which less than or equal to k. So what gives us this one? It means, how do we get this? How do we arrive to the answer? So what gives us this answer? It means we start the answer from Picard additive method. That's where we have y1 of x is equal to s naught of x f of x y n minus 1 ds. So this is the first steps. That is, we have shown that this lies on what? This function lies on what? On rectangle or on the domain. So the next step is to what? The next step is to prove that the inequality of this satisfied. We have yn minus 1 less than or equal to, we have absolute value of yn minus 1 is less than or equal to mk n minus 1 hn old series. So I'm going to upload this by send the statement because of our time, and for me to explain better, I'm going to use voice notes. Then I'm going to upload this with this video join so that you can continue explanatory. We are going to stop here for today's class. Thank you. You can see that you have proved that the functions lie in D. You can see from the notes that, as in the previous step, this shows that yn of s lies in D on R. Our R is the rectangle or domain, and hence our f of syn is divine and continuous on s naught minus h and s naught plus h. So our next step is to show that the inequalities satisfy that the induction. We now prove by the induction that the y of n minus yn of ny, the absolute value is less than or equal to mk to the power of n minus 1 n factorial s minus s naught and n at n is equal to 1. And you know that we have already verified that for n is equal to 1, we suppose the inequality is what? And if you check for what I got from there, that yn minus 1, yn minus 2, it means whenever we see n, we are going to put 1, we are going to test for 2. So that's why we have n minus 1, n minus 2. You can see that whenever we see n, we put n minus 1. So that's why we have n minus 2. Whenever we see n, s minus s naught raised to the power of n, the absolute value raised to the power of n. So whenever you see n, put n minus 1. That's why we get our inequality induction holding n minus 1 and n minus 2. You can see that that's why we have 1n minus 1n1 because it's our induction inequality that we want to prove. So we have the Lipschitz condition given as this. So that's why we have f of s yn minus 1 minus f of s yn minus 2 less than or equal to k y2 minus 1 1. So from there we prove that our mathematical induction also hold in this. If you go through the notes, you will see exactly what I do, that I also hold in the Lipschitz condition and also hold in what the induction in mathematical induction. So we now prove that if our n is approaching infinity, is convergent sequence. You can see that we are proving that if the sequence is converges uniformly, and if you look about this very well, what does we understand by convergent sequence? Whenever we are going to have another value, that if you check the volume, that you are using infinite series of, because of the induction mathematical induction rule, you are using it to find the convergent sequence on it. If you have proved that our uniformly it converge uniformly, then our next is to prove that if our y is equal to y of x, does it satisfy the derivative of y of x, that yx y prime is equal to f of x. So you can see from from the image that they prove that y dy over dx is equal to what, f of x comma y. And if you have satisfied this, it means that what the and you can see that they have proved it already. So that is the sequence of dy over dx equals to f of sy satisfy, and we have shown that the differential equation is satisfied. So next is to us to prove the last, that is, if the equation is satisfied, it means the equation that it is exists, and that is the theorem is what, existence, that is it exists. And next is to prove that does it satisfy uniqueness, that is it unique. That the differential equation satisfy the way over the s of f of xy or f of xy. And the last one, what they did there is what is the continuation on the existence. If the theory satisfy a unique, that is, if it is unique, you can see what they prove, that is, they proven for it, where we have a series, where we have a continuous, where we have the solution. If it is unique, and remember that if the solution is unique, then you have gotten an answer. You can see that from the series that we have there, that is convergence in the limits. And before, after the toss, we have the solution y of s is unique, that is, it satisfies the what? It satisfies the function that we have given to, it satisfies the limit, the function that we are set to prove, and it exists and unique.